Hello, my name is Jeanette Veldman, and I am from Central College. I've been working here at Ohio Wesleyan with Dr. Brad Trees and ZJ Poe. We have been studying optimal conditions for synchronization in Josephson junction arrays. I would first like to address the question, what is a Josephson junction, or for short, a JJ? A JJ is comprised of two superconductors, each with a correlating wave function and phase. These superconductors are placed approximately 1 micrometer apart, and the middle is filled with a non-superconducting barrier. Brian Josephson predicted that tunneling would occur and energy would not dissipate over this barrier. This was shortly after confirmed. The critical current is the maximum current that can flow through the junction for there to be no voltage drop. However, when the bias current is greater than the critical current, we see a voltage across the junction. This voltage follows the equation, voltage equals h bar over 2e d phi dt, where h bar is Planck's constant over 2 pi, and E is the fundamental charge, 1.6 times 10 to the negative 19th coulombs. We use a simple physical model for JJs called the resistively capacitively shunted junction model, the RCSJ model. The RCSJ model is comprised of 3 channels, the supercurrent channel, the resistive channel, and the capacitive channel. The supercurrent channel is described through the equation, current through the supercurrent equals the critical current times sine phi, where phi is the phase difference of the 2 superconductors. The resistive channel is described through basic Ohm's law. Current equals voltage over resistance. Substituting in our previous equation for voltage, we obtain our final equation, current equals h bar over 2er d phi dt. And lastly, we have our capacitive channel. Using the law, charge equals capacitance times voltage, we substitute in our equation for voltage and take the derivative of both sides, leading us to our final equation. The current through the capacitive channel equals h bar times c over 2e, the second derivative of phi with respect to t. When the bias current is greater than the critical current, the bias current is described by the sum of the behavior of the 3 functions, as seen in this equation. This is the governing equation for a JJ. This RCSJ equation can be applied to various JJ geometries. The most basic geometry is a single plaquette, as seen here. We make the RCSJ equation unitless for simplification purposes. Using conservation of charge and phase constraint, we develop a system of nonlinear differential equations. We numerically solve this system for the phase of each junction and the voltage of each junction. Using these results, we are able to calculate the phase order parameter. The phase order parameter measures the degree of synchronization within an array. We apply the phase order parameter to 3 geometries, the first geometry of which is the single plaquette. The 2 voltage active junctions in the single plaquette are coupled by 2 junctions with the same critical current. This critical current acts as the coupling strength. We develop a contour plot of phase order parameter as a function of coupling strength and bias current values. We are able to identify an area of synchronization. We apply this same technique to a double plaquette with a shunt junction. We found 2 contour plots of phase order parameter as a function of the bias current and coupling strength and the bias current and the critical current through the shunt junction. We were able to see 3 areas: an area of unsynchronization, an area where the left 2 voltage active junctions and the right 2 voltage active junctions are synchronized but separately, and we were able to identify an area where all 4 voltage active junctions were synchronized. The final geometry that we examined is a serial array with a shunt junction. We again were able to apply the phase order parameter to identify bias current and shunt junction critical current that create synchronization within the 2 voltage active serial arrays. We are able to apply the same process of phase order parameter to various other geometries. I would like to thank the NSF and Ohio Wesleyan University for their funding. Thank you.